Welcome to this video lecture on the subject optical and microengineering. So in this lecture we are going to discuss about optical sources, LED and ILD characteristics. So light sources used for optical fiber communication are light emitting diodes and injection laser diodes. So LED made from materials such as aluminum gallium arsenide and gallium arsenide phosphide. So these are the compound semiconductor materials which have the property of light emission. So light is emitted when the holes and electrons recombine. And ILD similar to construction of LED, but the ends are highly polished to reflect the photons back and forth. So first we shall discuss about light emitting diodes. So here we have a basic LED operation. So the normally empty conduction band of semiconductors populated by electrons injected into it by the forward current through the junction. So and the light is generated with the electrons recombined with the holes. So this is the mechanism by which the light is emitted from LED. So in this diagram we can see the symbol of the light emitting diode and the construction and the cross sectional view of the construction where p-type and n-type material is used. So in between we have an active region where the electrons and holes recombine to generate the light emission, and we have a substrate. The electrons are marked with the green color and the holes are marked with the red. So the light emitting diode, it is used for fiber optics. So it should have some characteristics such as high radiance, that is light intensity, and fast response time and high quantum efficiency. So some of the LED structures used in fiber optics are planar LED, dome LED and surface emitter LED and edge emitter LED. So we can see the basic LED operation. Here the PN junction acts as the active or recombination region. So when the PN junction is forward biased, the electrons and holes recombine either radiatively where it emits photons or non-radiatively by emitting the heat. So this is the simple LED operation. So in this diagram we can see the valence band and conduction band, and in this picture we also have a homo junction where p-type and n-type are same materials. So the emitted wavelength depends on the band gap energy. The transition takes place from any energy state in either band to any state in other band. So this results in the range of different wavelengths produced in this spontaneous emission. So this accounts for the fact that LEDs produce the range of wavelengths. So typically around the range is about 80 nanometer or so. So working of LED. So when the PN junction is forward biased as shown in this diagram, so the electrons and holes recombine in the active region to emit the light. So light is emitted at the site of carrier recombination, which is primarily close to the junction. So the amount of radiative recombination and the emission area within the structure is dependent upon the semiconductor materials used and the fabrication of the device. So emits incoherent light through spontaneous emission. It is used for multimode systems with 100 to 200 megabits per rate and broad spectral width and wide output pattern, and 850 nanometer region. It is the material used as gallium arsenide and aluminum gallium arsenide. For 1300 to 1550 nanometer region, the materials used are indium gallium arsenide phosphide and indium phosphide. So these are all the compound semiconductor materials, and we can see the homo junction. P-type and N-type are made from the same material, so this is known as the homo junction. So in this type of LEDs, carriers are not confined, so the light is not confined. So LED should have a high radiance or light intensity, fast response time and high quantum efficiency for fiber optic system. So next we shall see the heterojunction is the advanced junction design to reduce the diffraction loss in the optical cavity. So it is given by materials to control the index of refraction of the cavity and the width of the junction. So it depends on the refraction of index, depends on the impurity used and the doping level. So heterojunction region is actually lightly doped with the p-type material and has the highest index of refraction. The n-type material and the more heavily doped p-type material both have the lower indices of refraction. So this produces a light pipe effect that helps to confine the light to the active junction region. In the homojunction, our index of difference is low and the much light is lost. So double or single heterostructure junction with better light output is very much useful. So we can take the assessment. So first question is, which is used when the optical emission results from the application of the electric field? So the options are radiation, efficiency, electroluminescence, magnetron oscillator. So the answer is electroluminescence. So it is used when the optical emission results from the application of the electric field. Next question is, population inversion is obtained at a PN junction by which of the following? Heavy doping of p-type material, heavy doping of n-type material, and light doping of p-type material, heavy doping of both p-type and n-type material. So the answer is D. Thank you for listening this lecture.